Good morning. I am Krishna Kumar from Krishna's Classroom. We explore Riemann integration further. And where we left last time was the problem of interchange of integration with limiting process. Now, in that context, before I go to, in fact, I started with metric spaces and gave some idea, very brief idea of what a metric space is. And then that is the stage where we stopped. Now, before I take up the completeness problem, which was my objective at that time, and even today, that's the major theme. Let me just give an example which is in the context of interchange of limiting process and integration. So let me write down this example. This is the fourth example in that context, and I think I leave it for you to explore this. Let Fn from to R be defined by one if x not equal to k by 2 to the power n, and if x equal to k by 2 to the power n for some k comma 1 less than or equal to k 2 to the power n minus 1. Then this is defined for every n equal to 1, 2, 3. Then we have 0 less than or equal to f1x less than or equal to. In fact, it takes only two values, namely 0 and 1. It's a bounded sequence of functions. 0, 1. Secondly, since there are only finitely many discontinuities for each n, to see that Fn belongs to R0. It's Riemann integrable on the interval 0, 1. Now we look at the limit of this. What is the limit of So this is the first question. So explore this. Okay. Investigate. Limiting process integration. that's the second part. Also, in the context, you explore these class of functions. Is the limit is the convergence limit factor. F uniform. All these I need you to investigate. We have seen how these things are, and then analyze this example. In the context of the two theories. We have right. In fact, one of the little things that is the set k by 2 to the power n, k by 2 to the power n, or 1 2 to the power n minus 1, comma so I leave this problem to you, and it will be a good exercise for you to explore all of these things, especially, understanding the definition of uniform convergence and understanding a situation where a sequence is not uniformly convergent, what it means, and how one attempts a proof of that. I think I have discussed it in detail in the previous example. So I think you should put your hand on it and then experience how you write down or investigate various aspects of this example. So I just thought that I did. Okay, now we go to the problem of completeness. So we start with the following. Okay, let us write down the notation. The set of all F is a map from AB to R. It's a real valued map on AB, and F continuous on AB. That's the definition of CAB. All the space of all continuous functions. Now we define what is called a norm. Or length of f as a vector defined by given by I put a 1 here to distinguish from some other norm that we may use to discuss. Here the integration is in the Riemannian sense. First of all, is f Riemann integrable? You immediately see that f is Riemann integrable because it's a continuous function. All continuous functions are Riemann integrable. Therefore, it's a Riemann integrable function. If f is Riemann integrable, then mod f is Riemann integrable, and therefore this integral exists, and therefore this number is defined for each f. Okay. Now I have used some terminology called norm or length, which you may be already familiar with. Otherwise, let me just briefly recall what it is. Now you see, CAB is a, with the usual addition and scalar multiplication, is a vector space. It's a vector space over if you are dealing with complex valued functions, then of course C will be we can take the field to be C. It's a vector space over C also. Okay. Anyway, we are right now concerned only about the real valued functions, therefore it's a vector space over. Now, therefore, every continuous function is considered as a vector in this vector space. And we have defined norm f1 equal to integral a to b fx dx. So what is the norm? Now before we go into this, probably we look at R2. So you have a vector x and this is the vector. And you know that the addition rule is as vectors is a parallelogram law and so on. And you can associate with x its length. So we define it as, so for x we define associated non-negative number with it defined by the usual length concept, x1 square plus where x equal to x2. That's the usual Euclidean length of the vector. Now what does one do? See, we observe that this has the following properties. This function, so norm is essentially a function defined from R2 to R or R plus union 0 with the following properties. This is greater than or equal to 0. Norm x equal to 0 if and only if x equal to 0, then norm of Cx equal to mod C times norm of x, C belonging to x. Then you have norm of x plus y is less than or equal to norm of x plus norm of y. What does this mean? This means the following. Suppose x is this vector, y is another vector. Okay. If you take x, the length of x is a non-negative number, and this is equal to 0 if x equal to 0. Conversely, this is equal to 0 only if x equal to 0. So it's if and only if x equal to 0. Then Cx for any C is a scalar multiple of x, which either corresponds to an elongation or a contraction or even reversing the direction depending on C. And in that case, what happens is the length of norm of Cx is equal to mod C into norm x, or C belonging to R. And you also have norm of x plus y. Norm of x plus y is, what is x plus y? See, how do you get x plus y? You get x plus y by completing the parallelogram. So this is the vector. This is the vector x plus y. What you say is that the length of x plus y is less than or equal to the length of the vector x plus the length of the vector y. Okay? And these are the properties of the length function that you have. But there are other ways of introducing length functions, and I don't want to digress this talk to a discussion on norms. But this is the usual length that you are familiar with. And once you have the length, then you have, see, you can write b, let me write b2 x y norm of x minus y. Right here, because there are other things that are like b2, although we may not use it. Okay, this is the Euclidean distance that you have. You can show that this is a valid distance function or defines a metric. So R2 B2. Metric space, and one can do calculus or analysis on this topological space. It's a topological metric space. Okay, so if you want to use a sophisticated terminology, then R2 with this form is a topological vector space, and one can, you see that what you have is there are two structures there. One, of course, the algebraic structure is the linear space structure that you have, and then there is a concept of norm, okay, which endows the space with a metric. And you see that this is what you call a norm linear space. And there are other nice properties that you have, like whether a Cauchy sequence in R2 converges to a Cauchy sequence, a vector in R2 itself. Now this is the completeness problem. See that this space is complete, and so on. All those things one can prove. You can do analysis with no inhibitions on this particular space. Okay, I don't want to digress far too much into the normed linear spaces. I want to make just one remark. Possibly other norms one can introduce on the same R2. Okay, and R2 is the vector space properties are, it's a continuous, it's a yeah. Yeah, see, it's a vector space, it has a norm on it, so it's a normed linear space. So R2 is a normed linear space. And every normed linear space is a metric space. One remark I want to make at this stage is that if you want to define norm, then the space has to have a linear space structure. Because what is that you are doing here? You have two things for which you are writing down the norm. In fact, it's a non-linear, it's a linear space, therefore we are doing it. Because for a given x and a c, there is a cx, vector cx. So naturally, once you define norm of x, you start asking the question, what is how is it, how the norm of cx is related to norm of x. Well, that is answered here. And so also, what about the norm of x plus y? Because you know that x belongs to the normed linear, the linear space, so y belongs to linear space, then x plus y belongs to the linear space. So naturally you ask, what is going to be the norm of x plus y? And it satisfies the sort of triangular inequality that you have. Yeah. So this is the one that helps you to prove the triangular inequality for the metric. So show that this is a metric space. That is one of the exercises. Okay. Now we go to function spaces. One thing about this R2 that we have discussed is it's a finite dimensional vector space. Now the next question that you ask is, can you generalize? You can generalize it to Rn easily, or even Cn over C. You can generalize this whole concept, and that's all done. You can look into the literature. More or less everything works along the same lines. There is also, as I said, there is also a possibility that you can introduce the norm in very many different ways, because in that case what you look at is this, is norm is defined as a map from the space to R which satisfies these set of possibilities, namely norm of x is greater than or equal to 0, norm of x equal to 0 if and only if x equal to 0, norm of cx equal to mod c equal to norm x, norm of x plus y is less than or equal to norm x plus norm y. So any function satisfying these conditions will be called a norm. It's a legitimate norm, and in terms of this norm, it is also a metric space where the metric is automatically defined. So that's all fine. Okay. But however, so every normed linear space is a metric space. But to define a metric space, you do not require a linear space structure on the space. That's something that you can see. That's why I didn't mention about that last time. Now you see that CAB is a vector space with the usual addition and scalar multiplication. What is addition? Addition is f plus g at x. F plus g is defined by f plus g at x is equal to fx plus gx. And CF at x is defined by c times is c times fx. That is the addition and scalar multiplication. This is the usual addition and scalar multiplication. With this usual addition and scalar multiplication, CAB is a vector space over R. Right. Now we can introduce a norm. In fact, on this space we introduce two different norms and give a reading for this. Okay. So primarily in this talk we will be concentrating on CAB and we will not go to RAB. RAB we will consider as a stage. So we take CAB. In fact, we look at two different norms. One is called, let me just denote this by norm infinity, which I define as supremum of mod f of x for x belonging to. See, we are considering minus infinity less than a less than b less than infinity. So it's a compact interval that on which we are talking about the continuous functions, and there you see that each function f is bounded, therefore the supremum of fx exists. So this exists on since is compact. Compact means closed and bounded. Okay? And f is continuous. Now what you can prove is this. This satisfies all the conditions to call it a norm. So what do you have? You have to have this one. Greater than or equal to 0. That is clear. Then you have the second criteria, namely norm of CF mod C into, sorry, I think norm of f infinity equal to 0 internally if f is identical to 0. And let us examine this. What does it say? It says when f is identically equal to 0, this is supremum is equal to 0, therefore this is infinity. So that is defined. And now conversely, suppose norm f, the norm infinity of f is 0, then you see that supremum of mod fx for x belonging to this is equal to 0, and you see that we are working on continuous functions, therefore the function is identically 0. Therefore it is a well defined norm. So there is no problem about that. The third property is norm of CF, this is equal to mod C into norm of, that is straightforward, for C belonging to R. And the fourth property is norm of f plus b less than or equal to norm of f. Okay, let us ask what exactly is the norm in this case. Let's look at the graph of a function, of a continuous function on the interval. Now you see that the graph is contained in this band, stays in this particular band. That is the set of all points x f x lies on that. Let us take a very typical function. It's a continuous function that we are talking. Something like this. Now what you call the norm is the mod fx. What is mod fx in this case? Mod fx, you see that I am reflecting this back and something like this. Okay. This is the reflection of this portion. So the mod fx is this function, which is again a continuous function. This is the mod fx. Now you see, take the maximum value or the supremum of this function on the interval. So I think you go for the maximum of this function on this interval, which is somewhere here. So this height is what you call norm of. That's the norm. And you can easily see that norm of f equal to 0, then f is identically equal to 0, etc. etc. All these properties can be verified. I just display this function by this one. You will have this is the reflection of this portion over that. So that's the function. And this height is what you call norm of f h, norm infinity of f. This height from this number, this is what you call this number. That's right. And you can check all this. So this is one space. So CAB with sup norm, or what you call, this is called sup norm, is a normed linear space. That is one thing. With the same space, we can define another norm. The norm is this. This is one. Second norm is you take, there are several that you can define, that I can just mention. And you define norm f equal to 1. Which exists. Okay, so you know that f is Riemann integrable because it's continuous. Mod f is Riemann integrable. Therefore, this integral exists, and this integral we denote by norm f1. And then you can verify these things. 1 is greater than or equal to 0. 2 norm f1 is equal to 0 if and only if f is equal to 0. Now here the continuity is an important factor. Okay, because mod f is a non-negative function on the interval AB, and you know that any non-negative continuous function on the interval AB has its norm 1 equal to 0. That is integral a to b mod fx dx equal to 0 only if f is equal to, or implies f equal to 0. Okay. So this condition is satisfied because you can prove otherwise. If the integral is 0 and the function is not equal to 0, that is mod f is not equal to 0 at a point, then you can show that the integral would fail to satisfy this case. So that we can show. Third property is that is pretty straightforward. You should put a hand on this. That is it. Now let us see what this norm stands for. Once again, give a picture of what this norm is. So you have the interval AB on which there is the graph is lying in this band as before, and you are taking a continuous function. Now you see that what you are doing is mod f is to fold it back. So you have what you call its reflection over here. So you get a continuous function, and let me draw that function. That function is essentially this is mod f. Okay, this is mod f. This is mod f. Now you see that the integral of mod f is essentially this area. This is the integral of this area here. So that is a norm. And you prove that this could easily be a norm by appealing to the properties of continuous functions. Continuity is a very important factor in proving this. Right. So we will look at the space CAB with two different norms, namely norm infinity of f, that is the sup norm, and the so-called L1 norm. In both these cases, you will see what is the difference between what difference it makes for the space. Okay, because you are actually introducing a geometry on the space the moment you talk about that norm and a metric. Okay, the geometry turns out to be something different in both these spaces, and what difference it makes, it is really worth looking at. It's a sort of excursion into the area of functional analysis. But I thought maybe it's an opportunity to look at this and make some noise about it. Okay. Now we first consider one of the questions that we had opened up last time is this problem of completeness, namely what is completeness? If you have a convergible sequence of elements in CAB, okay, does the limit exist in CAB itself? Now this is the problem of completeness. So given a Cauchy sequence of functions Fn CAB with sup norm, namely see, thus the limit of such a sequence exists in short, what I am asking is this: I have a sequence of continuous functions on the interval A, and I am also assuming that it's a Cauchy sequence. That means it's a convertible sequence with respect to the norm and the metric that I have introduced. Question is, does it converge in the space itself? That means, can you say that all Cauchy sequences in the space converge to something in the space itself? Or is the space complete? This is the problem of completeness. Oh, I think we have defined it. So what do you mean by a Cauchy sequence? Let's recall. So we say that given epsilon such that for every n greater than epsilon, norm of Fn minus is less than. This is the criteria. This is what's called the quotient. What it says is that the distance between Fn and Ff gets closer and closer as n and f becomes larger. Or some stage onwards, all these functions in the sequence will come closer and closer. So the question that you have is it convergent? That means, what about the limit of this function? Sometimes the limit may exist, but the limit may not be a continuous function. You don't know until you prove it. Okay? So we will investigate this problem in this case. So it turns out that with this sup norm, CAB is complete. So let me write down the theorem. Try to prove this result. Okay. I just outline. Maybe you can write the details of this. What are the things to be proved? First of all, you have to show that it converges to something. So we start with the sequence. So let outline. Let so we claim that what are the questions that you have? Does there exists a limit of this sequence? Functions? Does it belong to if it exists? Belongs to or is it a continuous function? What the limiting function? Is it a continuous function? This is what we want to explore. Okay, first of all, let us look at this problem. So we are working on the interval. Okay. So what you have is a sequence of functions. Now first we hit on a limit for this set of functions. Now you see that Fn Cauchy implies Fn x is Cauchy for every x belonging to A. So these are numbers. You are fixing a x and see you have these functions. These are all the functions. So what you have is okay, what is the sequence that you get? This is x. So if this is f1, f2, f3, and then this number is f1 x, and this number is f2 x, and this number is f3 x. So you have in general such numbers. So for a fixed x you have such numbers, and they are numbers in R. Therefore, and they also form a Cauchy sequence, and that's quite easy to prove. I leave it to you to verify this. And you know that R is complete. Limit equal to x. And using this, define a function f on AB by f of x defined by limit x belongs to. So we have identified a possible limiting function. Once it's a convergent, once it's a quotient sequence. Okay, for each x you can define f of x, and it's uniquely defined. Therefore, now you can associate with each x in AB a number f of x, and that defines a function on AB. Okay, so the function is now defined. The next step is the following is f. That is f continuous for all x belonging to. This is the question that you ask. So what do? You just investigate this. Choose a point x and then neighboring point, etc., etc. So you choose x, y, maybe, and then estimate this. Estimate this. What do? You estimate this using this one. Fx minus fnx plus minus I'm just adding and subtracting. Okay. Now this, of course, these are numbers for fixed x and y. So you take x and y, x comma y. Now you estimate this. This is less than equal to okay. So you use now convergence to show that this can be arbitrarily small by choosing x and y close enough so that it is continuous. And what you do is you use convergence here. Use convergence here as well as convergence here, because you know that fnx converges to fx, fny converges to fy. Okay, so Given epsilon, you can make this less than epsilon by 3 by choosing n greater than or equal to some n1. And here this can be made less than epsilon by 3 for some n greater than or equal to n2. Okay? So this is simply using convergence. Okay? So for all n greater than or equal to n2, this is less than epsilon by 3. This is also less than epsilon by 3 for all n greater than or equal to n1 epsilon. The two numbers may be different. What about this? This you know that you have continuity of Fn, so that gives less than epsilon by 3 for mod delta, which depends on n. Okay? Depends on n as well as x and y and so on. Delta, which depends on epsilon, and yeah, depends on n and so on. So this is, you have a delta. Now what you have? Now you choose mod x minus y less than epsilon. So you see that you choose n, choose okay, then fix that n for which this is true. Therefore, you are assured that mod fx minus fnx is less than epsilon by 3, mod fny minus fy is less than epsilon by 3. That is assured. Okay. Now, what you have to do? You have to choose mod x minus y. Now, this is, you see, I think I should use this one, sorry. Infinity. Use infinity here, infinity here, infinity here. Yeah, okay. Right. Or what one does is the following. Yeah. You want to estimate this, the ref is continuous. This is. Now you see that you just find this. I'm sorry. We will start from that. And this is, of course, right? So you estimate this. Now what you have then is, you see that fx minus fnx is less than or equal to norm of is less than epsilon by 3 that we have for fixed x. Okay. So choose n greater than or equal to maximum of n1 and n2, and then choose x and y such that mod x minus y less than delta. Then you use norm, and then you see that this is less than or equal to this is less than or equal to infinity. In fact, twice this, because this term as well as this term, and this is less than 2 epsilon by 3 plus which is less than twice epsilon by 3 plus epsilon by 3 for mod x minus y less than, for mod x minus y. So what you do is you choose your n. Once you choose your n, then this can be worked out. Okay. So then you get mod fx minus fy is less than or equal to mod is less than or equal to epsilon provided mod x minus y is less than delta. Therefore, f is continuous. Okay, so you write the details of the proof. That's about a continuous. In short, it's a very clever way of estimating. Okay. So you are estimating this as less than or equal to the norm of this part, and mod fnx minus this part. This is the statement that you have. Okay, so this is the one that you are writing. So this is true, and then you choose n sufficiently large so that given epsilon, this is less than epsilon by 3, alright, and for that n you work this out. So the n that you choose has to be greater than the particular n that you have already chosen. Okay, that is the maximum of n1 greater than maximum of n1 and n2, and then you have this is less than twice epsilon by 3, and this because of the continuity of this, you can fix your delta such that for mod x minus y less than delta, mod fnx minus fny is less than epsilon by 3, so that this whole thing is less than epsilon. That's so. So we see that CAB is complete. Okay. So it's a complete matrix, but it has nothing to do with the integral that we have to use. Right? What we are interested in is what happens to this space with L1 norm. So the next theorem that we prove is that CAB is not complete. This is the answer. Okay. So what we want to prove is incompleteness of this space or non-completeness of this space And you know that the criteria for completeness is that every Cauchy sequence converges to an element in the space. So you have to show that the negation happens, and this is what happened in the first theorem. This is complete, where we actually proved that if you have a Cauchy sequence, there is a limit for that Cauchy sequence, and that limiting function is a continuous function. Here we are looking forward to proving that this is not complete. Now I will give an example. So it is enough to construct sufficient to construct an example that is a Cauchy sequence of CAD such that its limit is not a continuous function. So we start with the Cauchy sequence of functions. I mean, we use little bit of geometric intuition. What one does is we take the interval, take half here. Then we choose from here. Then construct a function which is identically 0 from 0 to half, and it's equal to 1 from half plus 1 by n. 1. Half plus 1 by n to 1, the function is defined to be 1, and in between it is linearly connected. That means you get a continuous function. So you call this a function. Okay, so let us define the function. Zero for x belonging to half. N into x minus half for half less than or equal to x and equal to 1 for half plus 1 by n. What? This is the definition of the function. You can check that at x equal to half, this function is fn is 0, and at x equal to half plus 1 by n, you see that the value of the function is equal to 1, and therefore what you see here is a continuous function. This continuous on the whole interval. So Fn take n greater than or equal to continuous functions. sequence of continuous functions belonging to it's a sequence of continuous functions belonging to this. Now, what I claim is that this is a Cauchy sequence. Before that, we make an observation. We let n tending to infinity. What happens? 1 by n goes to 0, which means half plus 1 by n goes towards this. And geometrically or intuitively, it must be clear that this function should tend to something like 0 on the interval 0 to half and 1 on the interval half to 1, and therefore there is a discontinuity at that point half. So your geometric intuition tells you that limit of this sequence is a discontinuous function. It is not anymore a C01 function. Okay, so this is what we do. So we have chosen the sequence already. The first investigation is Fn a Cauchy sequence. So what you have to do, you have to estimate this. Find out this norm of Fn minus Fm. What is this? This is equal to integral 0 to 1 Fn x minus dx. Okay. So let us draw the two functions. This is half. This is half plus by m. This is half plus by m. Okay. So let us work this function. So what are the functions? One function is 0 here, nothing changes on that part, and this is your effect. Your Fn is this. This is your Fn. Now let me draw the function Fm. What is Fm? Fm is essentially this thing. You are taking m greater than n. This is your Fm. This is your Fm. So we are taking m greater than n. Okay. So this is the continuous function. See, both are continuous functions. So what about integral Fnx minus Fmx dx over the interval 0, 1? You see that this is nothing but this area. This is the area. Okay. This is your Fmx and this is your Fn. Okay. So sorry, I think I have to mark it. Okay. So on this portion it is 0. So Fm is this one, and minus Fn is this one, and this is the area enclosed between these two. And then of course here it is 0, here it is 0. Okay? So what exactly is it? Can you estimate it? You can directly compute using the definition of Fn and integration. But one can easily see what exactly is it. Okay, so let me just mark this. So you see that even without performing the integration, you can estimate this particular area. So you see that this is you can actually work out the area of this region. It's not difficult because you see you can use rectangles and triangles and just take the difference and so on. Okay. So what one does is you compute the area of this portion and subtract from it the area of this. Okay. What is the area of this portion? This whole thing. This is equal to the area of this rectangle plus the area of this triangle. So that's equal to, so the desired area is actually triangle A, area of the triangle ABC. This is, and this is equal to the area of the region ABCD minus the area of the triangle ACB. Just you calculate, and that's quite easy to calculate. Okay, and the area of ABCD, this region is actually sum of the area of this rectangle. So triangle ABD plus the area of the rectangle EBCD. So you just estimate this. If you just estimate this, you can easily show that this is equal to, I need you to compute this, half of 1 by n minus 1 by n. I have chosen greater than or equal to n. This is the area that you get. And that you can obtain even by integration. So you do that, check that this is true. This is an easy way of seeing what it is using the geometry. And you see that this goes to 0 as m n goes to infinity. So you see that norm of which is equal to half of goes to 0 as n goes to infinity. Both n and n goes to infinity. Or this can be made arbitrarily small by choosing n sufficiently large and m greater than or equal to 10. This is hence Fn is this quotient with respect to norm 1. Now we want to prove that this does not converge to a continuous function. And these are the hand-on techniques that you use. You go to the geometry and all these things you should learn. Okay? You can as well estimate it. Using the integral. That's very easy. You know the definition of the function on this whole interval, and then take the difference and then estimate it and then arrive at the same result. I've just shown you what exactly is it. Okay. Now what we want to prove is that Fn does not converge to a converge to a converge to a continuous function. Okay, okay. So we can show that the limit exists, there is no problem. Okay, or rejects the limit exists, so you call this fx. Now we claim that f cannot be a continuous function. Okay, let us start working on this. What is f? This is the question. So for that, we first show that on the interval 0 to half it is equal to 0. So claim what do you do? To what purpose? F of x minus this you see is that less than or equal to integral 0 to 1 and you know that this goes to 0. Yes, that's the convergence as n tends to. Therefore, this implies integral 0 to half what does this mean? But f and x is identically equal to 0 on 0 half. Therefore, what do you get? It implies integral 0 to half and if f is a so f is a continuous function on the interval 0 to half and this is equal to 0. This is possible f is fx equal to 0 now what about the other part of the interval? On the other part of the interval, okay, what happens interesting this so on the path half to 1 this is fn. It's your fn. Now what you do is choose any x okay. Now we prove that fx equal to okay. So for that, now you see that you are choosing an x. So since x is greater than half, there exists an n naught such that x plus half plus 1 by n naught is less than x. This is possible. So you choose an x here, then you can always find an n naught such that this point is somewhere here. Okay, so for any x which is not equal to half or greater than half, you can always find this. Okay. Now we once again apply this. So you look at the problem on the interval 1 by half plus 1 by n naught to 1 of okay. You see that this is equal to 0. Why it is equal to 0? Because you see that since x is greater than half plus 1 by n naught, fn x equal to 1. Okay? Right? So if x is greater than if n is greater than n naught, then what happens? 1 by 2 plus 1 by n is less than this. So for n greater than n naught, you see that this is equal to 0. Right? For n greater than n naught, this is 0. Therefore, what you get? So you get by the same sort of argument that equal to 1 for x greater than 1 by 2 plus 1 by. Now, choice of x is arbitrary, which implies only condition that you have on x is that x is greater than half, which implies f of x is identically equal to 1 for x on the open interval 1. Therefore, what have we proved? We have proved that fx is identically equal to 0 on this one, fx is identically equal to 1 on this. Therefore, which implies f has a jump discontinuity at see here we are using this because we are again using this one integral 0 to 1 this is equal to 0. So we are using that actually. Therefore, it has a jump discontinuity at x equal to 1. Therefore, the limiting function is not continuous. Okay? So that's the problem. So if you assume there is such a function, then that function cannot be continuous. So a Cauchy sequence, there exists Cauchy sequences. What do we have? There exists which do not have limiting function in. So C01 is not common. That is not Therefore, in general, C A B is not complete. Or was assumed is C A B. That's the general. Okay. So you see that the change of norm and consequent change of metric has made things go wrong. Okay. So one of the questions that immediately come up in your mind is this. Is this sequence of functions that we have constructed, you know that it is in the L1 norm, it is not Cauchy. But is this, so this is the computational proof. Now the question that you ask is this sequence that's the next question. Let us investigate this. Again, we draw the graph. Now you see that this is 1 by 2 plus 1 by n, 1 by 2 plus 1 by n. So this is the function that you have. This is one function. The other one is, this is the other function. So you have, this corresponds to Fm, this corresponds to Fm. Now what is the norm here? Geometrically the norm is the distance between Fm and Fn, the vertical distance that you have between Fm and Fn. So it's the supremum of, you see what is the distance between these two functions? It is 0 here, 0 from here, that's clear. But in between, you know, it has got positive distance, something like this. It's not the area I'm marking out, it's the distance, vertical distance that you have. And it is the supremum of this one. And whether the question is, does this go to 0 as n and m goes to infinity? This is the question that you are asking. Okay? It's not clear because as n and m goes to infinity, what happens is both 1 by m goes to 0, 1 by m goes to 0. So this point moves this. So you get a sort of this norm giving you length. Now what I want to show is this, that this is not a Cauchy sequence. Okay, so how do I move that? Okay, so let me draw the graph. The graph of the function is this. This is one line, and this is half. This is half 1. Now you see that I take half plus 1 by n. So this is the function we have. This is the function. This is corresponding to the point half plus 1 by n. Now I take half plus 1 by here. So the function that you have is this. So you have two functions. One is this one, the other one is this one. So these are the two functions. So I will mark it with two different colors. So you have one function which is 0 here, then here, and then this is your. Now I have another function which is another function which is this one. So that I call F2. Okay. Now I compute the following. What is norm of it is the supremum of fnx minus f2nx x taken over 0 to 1. Now you see that if you carefully look at this is the kind of situation that you have. I just magnify the whole thing. So what I have is something like this. Okay. Again, because what is relevant is this portion. So I take 0, 1 by n and 1 by 2. Okay. What happens here? So here I have this is 1. So I have one function is like this, the other function is like this. Right? So I have to find out the vertical distances and so on. Now look at these two triangles O, A, B. This point is marked as C. Okay. So you work out the difference between these two functions. These are the graphs of the function on this interval. The relevant other place it is 0, so there is nothing coming there. It is not relevant. Okay, what happens here? So you look at these two triangles. So let me call A, B, C, D, and E if you want. It's irrelevant. So you look at these two triangles. These two triangles, you see that this is a line, these two lines are parallel. So you have this angle is equal to this angle. And this is of course right angle triangle. And what you have here is the distance here is 1 by 2n. And the distance here is also 1 by 2n. This is because it is 1 by n minus 1 by 2n. This is the distance. This is the distance here 1 by 2n. So this is the distance that you have. Therefore, you see that OD is equal to BA. Therefore, these two triangles are congruent. These two triangles are congruent means BC is equal to CD. So you have and you know that BC plus CD is equal to 1. Therefore, each one is equal to half. And that does not depend on n at all. This is independent of. So you see that norm of and this doesn't go to 0 no matter how large n you choose. Doesn't go to. Therefore, the sequence that you have constructed is not a Cauchy sequence in C01 with norm infinity. Okay, that is why there is no question of completeness problem or anything coming up there. Right? So, since this function, although this is a sequence of continuous functions, the sequence that you have chosen is not a Cauchy sequence with respect to one metric, whereas it is a Cauchy sequence with respect to another metric. Therefore, you have the question of completeness asked there, and there you have seen that it is not complete. So, the moral of the story is that the completeness property may differ depending on what norm you adopt or what metric you choose. This is an important thing. We have seen that C01 norm 1 is not complete. C01 with norm infinity is complete. Now this example does not fit into that realm, mainly because the sequence that you have chosen is not a Cauchy sequence. So there is no question of asking such completeness for that sequence. Okay? So this is about the completeness of CAB. Now what I want to take up then as the next step is the following. So we have seen CAB is not complete with respect to norm 1. So the problem is that the limits spill over and go outside this. So this is your CAB. You see that if you take a Cauchy sequence, you certainly would seek functions from outside to which it could possibly converge. As you have seen in this example, you end up chasing a sequence of continuous functions which is Cauchy in the L1 norm. You end up getting a discontinuous function as the limit. Okay? So the next question that you ask is, you take a larger linear space which contains CAB, something like RAB. You know that all continuous functions on AB are Riemann integrable. Therefore, CAB is contained in RAB. So RAB with now 1. Okay? Or the analog of that. You ask whether it is complete or not. This is the next question. Okay? You have some kind of a feeling that the space could be complete. Okay? But then, to your surprise, you see that the space is also not complete. So that's our next investigation. With a very sophisticated example, we prove that RAB with norm 1 is not complete. That leaves the field completely open to question the process of integration. Thank you very much.